Good morning, here we are. It's the physics video lecture. Physics 2A video lecture 23. We're talking about Newtonian gravity today. Let me review a bit and got some great material today. So let's see, we had ended up with the inverse square law, but I'll back up a little bit from that. So we're going to just call this Newtonian gravity. And I went through a pretty lengthy derivation to end up with the law of gravity. So we had circular orbits, and by the time Newton came around, Johann Kepler had figured out the laws of planetary orbits, but it was astronomy, it wasn't physics. But if you have a central body orbited by a little one, so I'm not using 1 and 2, I'm using capital and lowercase m now. Lowercase m is orbiting the central body. So Earth orbiting the sun, for instance. And you use the physics formalism that Newton invented. So circular orbits plus Kepler's law, Keplers Third Law, tells us that the force between the two objects F is proportional to the product of the two masses and inversely proportional to the square of the distance separating them. So this is what I ended with the other day. This is the inverse square law, and we have to do a bit to give this whole thing meaning. But the first thing we had was, because it was an orbit, circular orbit, we know the acceleration was towards the center. It was centripetal acceleration. So the first thing we have is that the force is an attractive force. Okay, it's an attractive force. And the idea is we have these two masses, and this time I'm going to label them 1 and 2. So M1 and M2, they're separated by a distance r, and regardless of whether they're orbiting each other or not, they're attracted towards each other. If you were just to place them here and let go, they would drift towards each other. Okay, it's an attractive force. There's the separation distance r. So the force, the direction of the force, remember force is a vector, the direction is along the line that is joining them. Okay, that's the direction of it. And we refer to that as a central force sometimes as well. We've got attractive force. And now we have to actually look a bit at this formula here. Namely, what does this inverse square business mean? Well, because it's in the denominator, it means that the greater the distance of separation, the weaker the force. Okay, so the force is stronger the closer together the objects are, and weaker as they go farther apart. So I can graph this magnitude of the force. So magnitude of the gravitational force. And if I graph this, and there's the separation distance and there's the force, then it is decreasing. So if it has a certain value at a certain distance here, then if I double that distance, I'm going to put 2r and square it. I'm going to have a factor of 4. So it's going to be 1/4. That's great. So out here I've doubled the distance, so I'll go down 1/4. And if I triple the distance, it'll be 1/9. So this curve goes down like that, gets very small. And if I go in, of course, it grows like that. Okay. So that's the shape of the inverse square curve. And like I said, any two masses, so what should I say next here? Okay, I have proportionality, so there is a proportionality constant that Newton himself did not even know yet. It was measured later. So the next thing I'll talk about is the proportionality constant. And that gets the letter capital G 6.67 times 10 to the minus 11. 10 to the minus 11 what, you might ask? Well, let's go ahead and look at the units of this thing here. So the proportionality constant makes our force law look like G m1 m2 over r squared. So now we know how to get units off of this thing. We solve for G, so that's F r squared over the product of the masses. Okay, I'll do this interchangeably, by the way. I'll either do the capital lowercase m or m1 and m2, doesn't matter. Okay, here's an r. And then we take the units. Okay. Make sure you know how to do this. So what do we have here? Units of force is the Newton, length meters squared, mass and another mass kilogram squared. So those are the units here. Newton meters squared per kilogram squared. And the question is, how was this proportionality constant discovered? Once you know this proportionality constant, you know a lot of things, as I'll show you in a moment. So the way it was discovered, I'll send this up here. So we'll title this next little section, very important one. We'll title it Measuring Capital G. Okay. Measuring capital G here. And so figure out how that is determined. The first name is Cavendish. So Cavendish constructed a torsional balance. What you guys should do is look up an image of the Cavendish torsional balance, and you can print it out and add it to your notes. The idea here, now the Cavendish balance is a little more difficult to draw, okay? And I'm just going to leave that there because the second method, which was after Cavendish, so Cavendish gets all the glory, okay, but a second worker named Jolly has a more transparent method of measuring G. And so this is the one I'm going to sketch for you. And the idea is to have a balance with two masses, two dense masses on the end. And this is just a normal balance here, okay? Imagine we've suspended this here, two masses, lowercase m, lowercase m. So it's balanced. And then what Jolly does is he wheels in a really large mass here. You can imagine this capital M, just for fun, we can imagine it's been wheeled in on a wheelbarrow because it's really massive. And you bring it in here, and by the law of gravitational attraction, you know, it didn't, I don't have a picture, it doesn't have to be a planet, it can just be two masses, so you can do this in the lab. By that law, we're going to have this thing tilt. So I'll draw this in red. It tilts a little, right? Because it's attracted, and to bring it back into place, you have to add a little delta M to this side. So if you add a little delta M, then it'll go back into balance because it's being attracted from this side. Now it's gravity, imagine it were magnetic or something, okay? This side is attracting, you have to add a little counterbalance on this side. So that brings it back into equilibrium. And then we have our measurements. Now, the separation distance we're going to call D between, let's see if we get a better pen here. Yeah, separation distance D, that's between the centers. So, distance between center, between the centers of these masses. And I'll put here delta M added to rebalance on this side here. And over here we have the attraction between these two masses. Okay. Attractive force. Okay. So now with Newton's law, we're ready to go. So the attractive force between these two masses over here, we have F is equal to G M over D squared now, because that's the separation distance. But that is simply equal to the added weight of this delta M that we put on here to rebalance it. So that's simply equal to this little delta M times G. By the way, this experiment, easy to describe, very, very sensitive and difficult to do because these forces are so weak, okay? But it can be done, it has been done. And the thing is now, this equation describes our experiment. Because if we now focus on this thing above the red bracket, the only unknown is capital G. So if you can set this up and make it work, then you measure the distance, you measure the two masses, the big one, the littler one. The delta M, you carefully measure that, the one you dropped over there, and G is our 9.8. Okay. So the only unknown in this equation is capital G, and that's how this was determined. So I'll write underneath here, two things. Important assumption. And the important assumption that I've already stated without being explicit about it is that the distance, the separation distance here in Newton's law of gravity is the center to center separation distance. Center of a spherical mass to the center of another spherical mass. Okay. So the assumption is that the spherical masses act like point masses gravitationally, because I'm just taking those points at the center. Okay. So they act as point masses. That's why we're center to center. And now the only unknown in equation star here is G, and we'll just solve for it. Delta M, so this is experimental. We've got a D squared, we've got the product, of these masses. So calculate that out and you arrive at this number here. Okay. Now I'm going to give applications. The ramifications of this are just endless. Okay. And we'll see really quickly what all we can do with this now. So once again, let me formulate Newton's law of gravity now. Now I'm going to call it universal gravitation. So after deriving this from the orbital data, Newton went ahead and hypothesized that this is a universal property of any masses anywhere. They're attracted towards each other across vast space, across vast distances, but also, as Cavendish and Joly showed, in the laboratory as well, at small distances. So universal gravitation. So now this time, I'll formulate it once and for all, and then give the examples. So any two masses exert an attractive force on each other. An attractive force on each other. Now we already know, we assume Newton's first law, second law, well, especially Newton's second and third laws, we assumed. So they exert an attractive force on each other, and again, I'm just going to draw M1 and M2 over here. They're separated by some distance, we'll call it R, and that force, like I said, it's attractive and it's equal to G M1, M2 over R squared. That many newtons. This G, of course, is a very small number. It's not a very large force. Good. Now here's the example that we're going to start things off with. Here we are. This is our Earth. We are standing up here on the surface of Earth. The Earth has a mass capital M, and our distance, in fact, I'll put a subscript E here, our distance from the center of Earth is the radius of Earth, and our mass is lowercase m. So now this assumption, the Earth is a giant sphere, of course, but it attracts us as though it were all concentrated at the center. It attracts us as though our separation distance is the distance from the surface to the center. So that being said, the force is equal to G, mass of Earth, mass of me, divided by radius of Earth squared. See how I'm using Newton's law here for that particular scenario? Mass of the Earth, mass of the person on the Earth, distance to the center of Earth squared. But if I'm standing, say, on a scale, then that scale is telling me that's the force. Okay. So the weight, this is my weight according to Newton's law of gravity. Now think about it. What is the only unknown in this equation here? It's the mass of the Earth. Okay. So just based on this discovery, Newton's law of gravity, and then Cavendish figured out what capital G is, we now have the mass of the Earth, I'll put E there, is equal to, Notice lowercase m cancels. So we have g radius of Earth squared divided by capital G. Is the mass of Earth. How are you going to figure out the mass of Earth anyway? The Earth's a sphere, but we don't know what's inside of it. Okay, nowadays we do, but principally standing up on the surface, we don't know what's inside the Earth. We don't know how massive the Earth is. Newton's law of gravity immediately tells us if you know the radius of Earth, you know g at the surface, you know capital G, you know the mass of that central body. Okay. M's cancel, make sure I didn't make a mistake here. G, radius of Earth squared, capital G. Yeah. So there's an example. And you could look up the data so you can find the mass of Earth in the chapter, these other numbers. In fact, you should probably do that just to convince yourself. These other numbers, you multiply them together, these are 9.8. Radius of Earth that we discovered earlier on, capital G, you get the mass of Earth. There's another version of this that I'd like to point out as well, really the same thing. And I recommend that you do this as well. I'm going to erase this right here. So once again, the equation up there at the top of the board, this one's just as fundamental. So solve the equation at the top for G. So what do we have there? G is equal to, again, the lowercase m's cancel, G mass of Earth over radius of Earth squared. Obviously, there are just equivalent ways of looking at it. This one I'd kind of like you to do. You should try this because this is a number we learned earlier, a natural constant, 9.8 meters per second squared. These are seemingly completely unrelated. This we discovered from the law of free fall. Okay. This here, if you take these data and calculate that number, you'll astoundingly actually just get that 9.8. Okay. It's equivalent to right here. It's a different way of looking at things. This is really important because it's the way to discover the mass of a central body. We're here on Earth. How do we know the mass of the sun, for instance? So that's going to be my next topic. Circular orbits and masses of central bodies. And yeah, it goes back to this thing right here. So this I'm going to erase now. We have it. And checking on the time. Oh man, I moved. Okay. So let me just put a note. Plug these numbers in. Talking about these right here to obtain 9.8 meters per second squared. That's important that you've done that before. Okay. Now, circular orbits and the mass of a central body. So now we're back to, I'll just call it capital M. We'll do a couple of these on the homework. Lowercase m. This could be the Earth orbiting the sun. So F equals ma. Okay. And then I'll put the G there first. Now, Newton's law. Now I'm going to put in Newton's law of gravity. Gmn over r squared, the radius of the orbit, equals mv squared over r, circular orbit, centrifugal acceleration. So we can simplify some things here. This goes away. One of these goes away. Then we're going to solve for capital M. M equals v squared times r. Okay. V squared cross multiply 1 power of r over divided by g. It could also, so if you had your orbital speed and your distance, it could also be 2 pi r over t, the quantity squared. That's my v squared times r over g. Okay. So the mass of the central body, right? I'm just drawing my conclusions here. So Newton's law, mass times centrifugal acceleration. Solve for the mass, cancels lowercase m is first, 1 power of r, v squared r divided by g. And then the v is 2 pi radius over period squared. So by the way, these are not formulas to memorize. What I'm showing is you can always start with this and work your way through. Okay, let's go ahead and see what we get here. So the mass of the central body is 4 pi squared. This is r squared times another, so r cubed divided by g times the period squared. So what we do now is send an orbiting satellite to a planet and take these data, or the planet, say Jupiter, has many moons around it, and so that's the radius of one of the orbits of a moon, and that's the period of its orbit. That'll give us the mass of the central body. So we got the mass of a central body just by standing on top, right here. Now, if it's a central body at a distance from us where we can't just stand on top, we have to take the orbital parameters of the satellites. So this is a satellite orbit, circular orbits, satellites, and these are the orbital parameters there. That's the radius of the orbit, that's the period of the orbit. R equals radius of the orbit, t is equal to the period of the orbit. So I'm going to assign a few problems like that, but make sure you always start here, okay? Because you may be asking for some different quantity. If you want the mass, you'll go here. You know, you may be given different things, so it's always principally, it's already right here. This substitution, of course, is just distance over time for the speed of an orbit. Okay. So this, by the way, is how all of these central body masses are known. That's how we know the mass of our sun. For our sun, this is the distance to the sun in meters cubed, and this is 365 days expressed in seconds and then squared. Okay. So you could have a little fun calculating some of these things and verifying the values that are given in the astronomical tables. Yeah, that's how we know the masses of Jupiter and Saturn and all these other bodies, okay? Because Jupiter and Saturn have many moons, and you can just check them again and again and again, and they all give you the same central mass. Okay, that is an important lesson. So we'll assign a couple of those. Oh, yeah, one more thing. This, of course, actually contains Kepler's third law. Let me make sure I show you that. We plugged Kepler's third law in to Newton's law in order to derive Newton's law of gravity. So we certainly will get it back out again. And I just have to rearrange this. Okay, so this equation here, I'm going to solve for t squared on the right. So, important note with what I'm doing up here, Kepler's third law is contained in this calculation, namely t squared equals, we're just going to solve for t squared up there. We're going to have 4 pi squared over gm times r cubed. T squared proportional to r cubed, right? T squared proportional to the semi-major axis cubed. Circle for a circle, this is it. And so when Kepler found his law, he found the ratio of these two were always equal to the same number. He didn't know g, he didn't know the mass of the sun, but it turns out that that's what this ratio was here. If you take t squared divided by r cubed, you just ended up with my expression in parentheses here. But the same thing holds true if instead of the sun, you're talking about the moons of Jupiter. Then you measure the periods and the orbital parameters of the moons of Jupiter, and every one of them, that ratio will give you this number, 4 pi squared g, but now the mass will be the mass of Jupiter. So this is always the mass of the central body. Back when Kepler was doing his work, the only central body that was being talked about was the sun. By the time Newton came around, the moons of Jupiter and some of their parameters were already known. And then he was able to test these ideas on Jupiter as well. Okay. So we'll practice these on some homework problems. And always remember, you can just set it up using Newton's law. Okay, work your way down. Okay, so there's one more major topic. In this chapter for us, before we move on to the next one. And this is, we're going to call it Newtonian gravity and energy. Okay. We're also going to have conservation of energy, but we need the potential energy of Newtonian gravity. So recall potential energy at the surface of Earth. So right here in this room, we can say, okay, here's the surface of Earth, here's the y-axis, and then we say potential energy due to gravity, mgy, which is the distance above the surface of Earth. Okay, so we're used to that. Now this is for the situation where the Earth is essentially flat under our feet. Now the question is, what if we're looking at the Earth as a whole? Okay. So for Earth as an entire sphere, here's our Earth, and then we're always some distance r away from the center of Earth. Okay. If we're standing on the top, right on the surface, then this distance is actually just the radius of Earth, but otherwise we're above it some distance. And so for Earth as a sphere, we have potential energy, use the same letter, is minus G. So we'll put a little m here, capital M here, over the distance. So this is something completely different, okay? Seemingly completely different. And I'm going to explain this a bit. It comes about by integrating the force law, and we're not doing integrations in this class, really. So I just kind of have to give it to you. Okay. But I will explain it and what it means for conservation of energy and everything like that. But first I have to resolve this very different looking expression. Okay, let's erase this right here. We'll do a graph for each one. So we're going to do the graph for this one first. And because of the minus sign here, by the way, the minus sign is crucial. We have to leave some room under the axis, because it's essentially a 1 over r behavior with a minus sign in front. So it's like this. Okay. And if we call this the radius of Earth, since we're talking about the Earth sometimes too, then we see that this is an increasing function of the distance going away from the center of Earth. Okay, it's an increasing function moving away from Earth, and in fact, this thing is too. So this graph here, which belongs to the upper picture, if I want to have use of G as a function of y, well, y is the distance above the center, above the surface of Earth, and so this one would have a slope like that. Okay? And what it means is that this slope and the slope of my red line here are the same. Okay? But the behavior is, if you go far enough away from the surface of Earth, the potential energy and the force get smaller and smaller. So yeah, these things have an interesting mathematical relation to each other. But what we're going to do with this is discuss it now in the context of energy conservation. So this is the potential energy of gravity. Go ahead and label that potential energy or gravitational potential energy. Okay. That's this one right here, and there's its graph. Okay, are we running out of time? Yeah, we got this. So this we'll call gravitational potential energy and escape speed. Now we're just going to call this conservation of energy. Now we have an expression for potential energy, so we can do conservation of energy in the following situation. Example of vertical launch. Okay, we like doing the vertical throw. Now we're doing a vertical launch, say some kind of rocket. So we're on the surface of Earth. or some central body with radius r and capital M, and we're about to launch our rocket from point A out up here. Okay, there's my rocket out here at point B. Point B. So here's how we do it. Energy at A is equal to energy at B. 1/2 mv sub A squared minus gmm over r sub A is equal to 1/2 mv sub B squared minus gmm over r sub B. You'll notice I've just done our recipe for kinetic plus potential. However, that potential has an intrinsic minus sign in front of it. If you lose the minus sign, you'll make a mistake. So that's kinetic plus potential equals kinetic plus potential. And now we're going to do an example of launching from the surface of Earth and launching all the way out to infinity. So this here is the general statement for energy conservation around a central body, or just with respect to Newtonian gravity. So now let r sub A be equal to the radius of Earth, because we're launching from the surface of Earth, and v sub B equals 0 at r sub B equals or going to infinity. So what we're saying is we can launch a rocket, and if we launch it with the right speed, it'll come to a stop out at infinity. Okay? It'll leave the Earth and never return. Unlike when you throw things up and they come back down. Okay? So this is interesting. What that does is it makes the right side of this equation equal to 0. And now we have 1/2 m v sub A squared minus g capital M lowercase m over Earth's radius is equal to 0. So this speed is the escape speed. So v sub A, and I'll say that it's the escape speed. V sub A is equal to, just by canceling the m's and cross multiplying over with a 2g mass of Earth divided by the radius of Earth. Take the square root. Now this is one you guys should also look up and plug in. It's approximately 11,200 meters per second. So it's a bit higher than the orbital speed I talked about the other day. It's actually the square root of 2 times the orbital speed, as a matter of fact. And that's called the escape speed. So yeah, with this new formalism, we get all kinds of interesting stuff here. With the potential energy of that form, which I've just written down here a couple times, we get the escape speed. Okay, good. Let's leave it at that and do some homework problems. I had a lot of these written down for you. Let's see. Should we do them all? I'll strike one of them. Okay, I have some really good problems here. So chapter 7, 33, 39, 43, and 44. Chapter 7. by the way, what homework is this? Number 23, so I'll just write this down. Homework 23, chapter 7, problems 33, 39, 43, and 44. Okay, try these, ask me about them next week too, and remind me to do some of these for you. These are really good. Nothing too fancy, but they're good. And they've all been set up for you in the course of today's lecture. They're circular orbits, and one of them is an energy problem that's really like setting this one up. Okay, so enjoy. We'll see you guys next time.